One day, your system crashes. Users can't log in, orders can't be paid, and the server keeps firing alerts. So you do what every developer would do, open the logs. Then you see 100,000 lines, 1 million lines, or even 10 million lines of logs. They are filled with error, warning, timeout, failed. It looks like you have a huge amount of information, but after a few minutes, you discover an even more terrifying problem. You still don't know what happened. There are plenty of logs, but they can't tell you the answer. Why is that? Because in complex software, logs record events. What developers really need is a story. Suppose you are developing a simple program. The user clicks a button, the program executes a function, and then accesses the database. But if the database connection fails, you see database connection failed. Basically, you know where the problem is. Because the system is simple enough. There's only one execution flow and one error path. But today's software is completely different. A modern application might look like this. A user request first goes through an API gateway, then sequentially enters the user service, order service, payment service, and inventory service. Finally, it accesses the database. A simple purchase operation passes through a dozen or even dozens of components. So how do you determine where the problem really is? You open the logs, and you find that the order service, payment service, and database all have logs. But the question is, do they belong to the same request? You don't know. What happened before the payment failure? You don't know. Why did the database suddenly time out? You also don't know. These logs are all correct, but they have no connection to each other. This is the hardest part of debugging large software. It's not that there is no data, but that there is no context. Look at this error message. What use is this sentence? It only tells you that the database connection failed, but it doesn't tell you which user, which request, which server, when did it happen, what happened before. In fact, a payment failure can have many causes. It could be that the bank card was declined. It could be that the third-party payment service is abnormal. It could be a network timeout. It could also be a database write failure. This log line only tells you the outcome is bad, but it doesn't tell you why it is bad. A truly valuable log should contain more information. Look at this log line on the screen. You can also see the difference. The error message becomes meaningful because you not only know that an error occurred, you also know who it belongs to, where it occurred, and what happened before it occurred. That is the information really needed for debugging. But in distributed systems, there is an even bigger problem. That is time. A request may pass through many services. If all services have their own logs, you need to manually piece this information together. It's like investigating a crime scene. You see a footprint, a broken window, a piece of surveillance footage. But you need to answer, do they belong to the same event? So modern systems introduce a concept, distributed tracing. Simply put, logs tell you that an exception occurred here, and trace tells you what this request went through from start to finish. For example, still the user request. First, it goes through API gateway, then sequentially enters the user service, order service, payment service, and inventory service. Trace can connect the entire path. You no longer see 100 isolated events. Instead, you see one complete story. However, even with logs, monitoring, and tracing, problems in large software are still very hard to solve because the reasons for a system failure can be many. It could be a sudden spike in CPU usage. It could be a memory leak. It could be slow database queries. It could be network latency. It could be thread contention. It could even be a line of code that looks perfectly normal. For example, a program crashes occasionally and runs fine 99% of the time. You check the logs and find no errors. Why? Because the real problem might lie in memory access, thread execution order, cache coherency, or an extremely rare boundary condition. This is also why large-scale software development is becoming increasingly difficult. The code itself is only part of the system. What is truly complex is the environment in which the code runs. This is also why future developers will need more than just coding ability. Artificial intelligence can help you generate code. It can help you complete functions. It can help you implement a feature. But when a software system with millions of lines of code exhibits a strange problem, why does a small change cause the entire system to behave abnormally? These are issues that generating more code cannot solve. You need to know what the CPU is doing, how memory works, how the network transmits, and how different components interact. You need to understand why the system fails. Because debugging complex software is essentially not about finding errors, but about understanding the system, and then reconstructing the process of what happened from a large number of fragments. Software is becoming more and more complex, and tools will become smarter. But people who can understand complex systems will still be very important.